Hello calculus fans, and welcome to section 2.5 where we study continuity. Continuity is an important concept in calculus as we study continuous functions in calculus. And continuous is like what you would think of in everyday language. A continuous process is one that takes place without interruption. So graphs of continuous functions are smoother graphs. They don't have holes in them or jumps in them. And it's like when you were in algebra class and your teacher would tell you, you can tell you're looking at a graph of a continuous function if you can draw the graph without lifting your pencil. So these kind of functions are very important in calculus, and that's what we study. Now, some of you will study sort of the opposite of that if you take discrete math courses. And if you're going into computer science, computer engineering, you will probably take some discrete math courses like discrete math or discrete structures. These classes study functions with distinct and separate values, so things are not connected or continuous. But today we are going to look at continuous functions. We learned in section 2.3 that the limit of a function as x approaches a can often be found simply by calculating the value of the function at a. So we just had to basically plug in that value into the function. Functions with this property are called continuous at a. I've got a little definition here. It says a function f is continuous at a number a if the limit as x approaches a of that function is equal to the value of the function at a. So if you take the limit as x approaches a of this function, you get exactly the same thing as if you just plug the value into the function. This definition implicitly requires three things if the function is continuous at a. And you can see that this makes sense. If this is true, then of course the function would have to be defined at a, so a is in the domain of the function. The limit would have to exist, because if this is true, if for this to be true, the limit has to exist. And then of course the limit as x approaches a of f of x equals f of a. So basically what it means is this: if we've got a function continuous at this point a, then the limit as x approaches a of f of x equals f of a. So what that means is all we really need to do is just use direct substitution. So direct substitution may be used to evaluate the limit. So we don't have to go through all those limit laws and really take a whole lot of time to figure out the limit. All we have to do is substitute this in. So this is really nice. To find the limit, as long as that function that we're evaluating is continuous at a, we don't have to use any limit laws or go through any of that. We can just plug it in direct substitution, which saves a ton of time. Also, the graph of a continuous function contains no holes, jumps, or breaks. So it's like that definition you heard probably in high school algebra, where your teacher would say, you can draw the graph of a continuous function without lifting your pencil. So if you can draw this graph, you're going through here and I don't have to lift my pencil, that just shows that on that domain, this function is continuous. So go ahead and sketch this picture a second if you would. Get this, it's a graph of a very strange looking function. But I want to talk about this graph. So if you look at this graph and think about what we set up here, the graph of a continuous function contains no holes, jumps, or breaks. You can see that there's a lot of problems here. So looking at this function, we can see it's discontinuous at 1, because there's a jump here. Discontinuous at 2, because there's a hole in the graph. Remember, these open circles just mean that the function is not defined at that point. So at 2, the function is actually defined, but it's defined up here. But as far as the graph goes, there's a hole in the graph here. And then we've got a problem at 4, where this graph comes down here, but it doesn't quite get to 4, then it jumps over here. So that f of 4 is equal to, looks like 1/2. So we've got these discontinuities at 1, 2, and 4. But we can talk about things being continuous from the right or from the left. So this one turns out to be continuous from the right at 1, which means that as we come in from the right on the number line, so we're coming in from the right, we're approaching 1 from the right. So as x approaches 1, the function's following the curve up here. So as x approaches 1, f of x is up here. So we can see that as x approaches 1, the function is approaching 1 also, right? So the limit as x approaches 1 from the left of this function is 1. Also, f of 1 is 1. So we've got this. We can say that this function is continuous from the right at x equals 1. Because of this, the limit as x approaches 1 from the right. Remember the plus sign up here, it's like a superscript 1, or superscript plus sign, means the limit as x approaches 1 from the right of this function equals f of 1. So x is approaching 1, x is coming in here, right? As x approaches 1, f of x, the limit as x approaches 1 from the right of this function equals 1. You can see we can make this as close to 1 as we want, right? The y value 1. Also, f of 1, if I plug in 1 into the function, I also get a 1. So because this is true, we can say that this function is continuous from the right. So it's discontinuous at 1, but it's continuous from the right at 1. The reason it's discontinuous at 1, though, is from the left is not continuous at 1. So as x approaches 1 from the left, the function is approaching 0, but f of 1 is 1. So because those don't match up, it's discontinuous from the left, which makes it discontinuous at 1. So this one is discontinuous at 1, but it happens to be continuous from the right at 1. One thing you may have noticed is that for a function to be continuous at a point, it has to be continuous from the left and also from the right at that point. The things that we study, the physical phenomena, are usually continuous, at least at our macroscopic level. Now it turns out that things are most likely quite different at the quantum level, but at the level that we interact with the world, typically physical phenomena are continuous. So as an example, let's say you drive a car from 0 to, let's say you're heading to class. It's your favorite class, of course, calculus. And you're like, there's no way I'm going to be late for class. But the only way you can make it there on time is if for a little bit of your trip you drive at 95 miles per hour. And of course it'll be worth it because you're in a big hurry to get your favorite class. So you're going from 0 to 95 miles per hour. Well, is there any way that you didn't at least for an instant hit 54 miles per hour on your trip? I mean, isn't it true that if you went from 0 to 95 miles per hour, you definitely were, at least for an instant, traveling at 54 miles per hour, right? You can't just, like, warp right over that, right? You can't, like, jump over that and go, well, I was going 53, then I instantaneously hit 55. Like, that doesn't work that way, right? At least for an instant, you hit 54. So this is a continuous process. When you went from 0 to 95 miles per hour, at least for an instant, you hit every real number in between here, right? At least for an instant. Or, you know, as a child grows, let's say a child grows in height or weight. So if you have a child growing, and let's say that your child hits 4 feet tall. Well, doesn't that mean at some point your child would have been 3'3" at some point on the way to get to 4 feet? So these are the kind of things we study, and this can be modeled really well with continuous functions, which is why we're going to study calculus. Or actually, we already are studying calculus. And of course, discontinuities do exist. So a really easy example is an electric current. There's something called the Heaviside function. So those of you going into electrical engineering will study this. It is mentioned in our textbook if you want to take a look at it. If you have the 8th edition of the book, it's on page 87. If you have the 9th edition, it's on page 86. And variations of this are used to study signal processing or in digital communications where you have a bunch of like ons and offs or ones and zeros that you can use to create information. Here's another example of a parking meter. Let's say this parking meter only takes quarters and it's 25 cents for every 15 minutes. So you'd have this step function like this. So it's definitely discontinuous. So at every 15-minute interval, there's a jump, right? It jumps up. So there are discontinuities that exist, of course. For the most part in calculus, we avoid the spots that are discontinuous. We concentrate on the places in the function that are continuous. There are different types of discontinuities and they have names. And again, it's not going to be a huge part of calculus because the functions that we study will be continuous, or where they have discontinuities, we will typically avoid them. So we have to know where they exist, and sometimes in Calc 1 and Calc 2 we use limits to get around these discontinuities. But let's look at the names of these. So here's some pictures of these types of discontinuities. The first type is removable. And it's said to be removable because we could fix it if we redefine this function at this point to, say, fill in the hole here. Remember, this hole just means there's just one point missing in this graph. So if we redefine this point here to fill the hole, then it would be continuous. Same thing here, if we redefine this point to fill the hole, it would be continuous. So this is said to be a removable discontinuity. And then these two are pretty self-explanatory. Jump discontinuity because the graph at this point jumps up here, so it's definitely not continuous. And infinite discontinuity because they don't connect here. So remember, discontinuity is just where there's like a hole or a jump or a break in the graph. So we talked about continuity at endpoints a little bit in an earlier example, but just to make this formal, I'm just going to fill in the blanks here. So this says a function f is continuous from the right. So remember, from the right means we're approaching the number from the right on the number line, right on the number line. So continuous from the right, add a number a if the limit as x approaches a from the right of the function is equal to f of a. So the limit equals the same thing as if you were to take the a and just plug it into the function. And likewise, the function f is continuous from the left at a number a if the limit as x approaches a from the left of f of x equals f of a. A little note about notation. You have to be careful here. If I put the negative in front of here, it's a completely different thing. So details are always going to be important for us. So we can't be sloppy with these details. This says x approaches a from the left. If I put the negative in front of here, then it means x approaches negative a. So just a little note, we always have to be careful about the details. As we mentioned earlier, evaluating limits of continuous functions can be done very quickly. Very quickly because really all we have to do is plug in the number. So this is really nice. If we're evaluating limits of continuous functions, we don't have to use the limit laws. We can basically just plug in the number. So it's really nice. We just plug in the number. The good news for us is that pretty much every function you've ever seen is a continuous function on its domain. So let's take a look at these. So this says the following types of functions are continuous at every number in their domains. So I'm going to list these off. So polynomials. So polynomials are the nicest functions to use. We'll see later they're differentiable everywhere. They have antiderivatives everywhere. But basically a polynomial, remember, is a number where the power is a non-negative integer. Right? So there's the cubics, the quadratics, anything that has a non-negative integer power is a polynomial. And they are continuous at every number in their domains. and their domains are all real, so they're continuous everywhere. Another one is rational functions. Well, a rational function is just a polynomial divided by a polynomial. So let's see, the third one here, we've got root functions. So square roots, cube roots, things like that. Those are continuous at every number in their domains. Okay, has your favorite function been mentioned yet or not yet? If it hasn't been yet, this could be the one. This could be your favorite. Trig functions. Okay, I'm just going to use a little abbreviation here. Everybody can interpret this, right? Functions. Trig functions, trigonometric functions, these are continuous at every number in their domain. So if you take a limit of a trig function, as long as the limiting value is a number in its domain, you can just plug it in. But we would not feel good if we didn't also have the inverse trig functions, right? Inverse trig functions. And what about exponential functions? Okay, we've mentioned most of the functions we've used ever since algebra, right? What's missing? Logarithms. Okay, logarithms. So any of these functions, which these are most of the functions we run into in everyday life, right? Most of the functions we've used up until this point, these are all continuous at every number in their domains. But it even gets better, because it also turns out that when you combine continuous functions with plus, minus, times, divide, or even with function composition, that's where you plug a function into another function. These also result in a function continuous at every number in their domain. So function composition, like f of g of x, right? Or maybe you had that this weird notation, f circle g, fog, and goff, which is a notation that I wish you would get rid of, because this function, this notation makes sense. It looks like you're taking g of x and plugging it into f. With this, you have to learn what that means. So these mean the same thing, but this is, in my opinion, much better notation. But anyway, function composition also. So we can take these functions up here and combine them in ordinary ways in function composition or with mathematical operations, and still we get a function continuous at every number in its domain. Then there's a note here. The inverse function of any continuous one-to-one function is also continuous. So one-to-one function, remember, this just means it passes the horizontal line test. So if you want a function to have its inverse, first it has to pass the horizontal line test. So the inverse function of any continuous one-to-one function is also continuous. The intermediate value theorem is an important theorem in calculus. It's used to prove other important theorems, but it also has a practical use. And this used to be used a lot more often before we had computers available everywhere with apps that could solve pretty much any equation. There was an algorithm you could use based on intermediate value theorem. It's actually called the bisect method. So when computers were first coming out, you would typically learn your first coding language you would learn was a basic language. And even with graphing calculators, when they came out, they had a basic language interpreter. And if you had to solve an equation, you could pretty easily write up a little code using the bisect method, which would allow you to use the intermediate value theorem, even though you might not realize you were using that, but you would use that in order to solve these equations to whatever tolerance you needed to solve them for. Nowadays, it's much easier to solve these tricky equations because there are software applications available almost everywhere. But let's take a look at this intermediate value theorem and see what it says. So it says, suppose f is continuous on the closed interval ab. So here's this function f, continuous on this closed interval ab. And let n be any number between f of a and f of b. So n is going to be some number here. So let's just put n right here. So here's n. N is some number between f of a and f of b. And then it says there exists a number c in this open interval a, b, such that f of c equals n. All right, and you'll see by this picture, this is not some kind of earth-shattering theorem. It's an important theorem, but it's pretty intuitive also. So if I go over here to this point and then drop down here, it just says there's this c in here. So it basically says that if this is continuous and n is any number, so I could pick any number between f of a and f of b, any number, and there will be a c that corresponds to that, where f of c equals n. So the takeaway is just this. The intermediate value theorem states that a continuous function takes on every value between f of a and f of b. So every one of these y coordinates between f of a and f of b, if this function is continuous, it takes on all of these values. We can use this to help us solve equations or to show where an equation has a solution. So let's take a look at an example and see how we put this to use. So this first example says, show there's a root of the function. Here's a function here between 0 and 1. So by root, what we mean is there is a solution. Like if I set this equal to 0, there will be a solution to that equation, or a 0, or basically just show if I were to graph this, it will cross the x-axis between 0 and 1. Right? We want to show that there is some solution. If I set this equal to 0 and I'm asked to solve it, there's some solution between 0 and 1. So a root of this function between 0 and 1. And we can see this is just a polynomial. And we know that polynomials are continuous on their domains. And of course the domain here is all real numbers. So it's continuous everywhere. So there's no gaps or jumps. So to show there's a root of this function between 0 and 1, I could do this. I could say, well, what is f of 0? What is f of 1? And here's how we'll make this work. So if I plug in a 0 into the function, so f of 0, I plug in a 0, 0, 0, I end up with a negative 5. So f of 0 is negative 5. And if I plug in a 1 for all the x's, I'll find out that f of 1 is equal to 13. I also know this is continuous. So according to the intermediate value theorem, there'll be a point C between 0 and 1 that takes on every value between negative 5 and 13. So looking at this picture, we've got f of 0 is a negative 5, f of 1 is 13. I don't know what the graph does after these points. I just drew this to show that it continues. Now we know that we've got a continuous function. And it's continuous, it's a polynomial, so it's continuous everywhere on its domain, and its domain is all real numbers. So it's continuous everywhere. So it doesn't have any jumps or gaps or anything like that. So we know that this function between 0 and 1, these have to connect somehow. We know they connect. So let's just say we've got, we know that somewhere along here this connects, right? There is some point C here. There's some point C where this function crosses the x-axis because it's negative 5 at 0, it's 1 at 13, it's continuous, so these have to connect. It's also a function, so it can't like wave around here. It's a polynomial, it's a function continuous everywhere. So we know there's some point C where this connects. And so the way that we can show there's a root of this function between 0 and 1 is this. Just show that using the intermediate value theorem, there's a point C here that takes on every value from negative 5 to 13. So negative 4, pi, 6, they're all included, but the one we want, the one that's a root, is where f of c equals 0. So what we can say is we can say this, we can say f of 0 is negative 5, which is a negative number, it's less than 0. F of 1 is 13, which is greater than 0, it's a positive number, which means that there's some c here such f of c equals exactly 0, because we're going from negative to positive, so we have to hit a 0. And we can make the argument like this. We could just say we're basically using these two facts, and we can say therefore, and I use this notation you see a lot of times in mathematical arguments. It just means therefore. Therefore, by the intermediate value theorem, there exists a point C in this open interval 0 to 1 such that f of c equals 0. So that's our argument. We see we've got a negative here, we've got a positive here. We know it's continuous, so there has to be some c in between here that such a f of c equals exactly 0. So we just say by the intermediate value theorem, there exists a point C in this interval 0, 1 such a f of c equals 0. Graphing calculators actually use this theorem also. So when you're graphing a function, the graphing calculator doesn't actually calculate every single pixel. They connect a lot of pixels by just turning on intermediate pixels as they make the graph. But I'll tell you how this was used before. I had mentioned the bisect method in programming. So let me just mention this real quick and show you what we used to have to do. The bisect method. So let's say we wanted to find this root. So far we know that the root exists, right? We know that there is some root in here between 0 and 1. So with the bisect method, what you would do is once we got these points, we would pick a point halfway in between. So we know we got a negative here and a positive here. So once we find that, so we know there's a 0 in between here, we pick the midway point. So we would say, like with the bisect method, we'd say, okay, so f of 1/2, right? I'm going to go right in between these two. And f of 1/2, so I plug in 1/2 into the function up here, and I get f of 1/2 equals 2.9375. Well, this is a positive number. So then I go over here and I go, okay, so f of 0 is negative, f of 1/2 is positive, so now I know the root is between 0 and 1/2, so I'm narrowing it down. So again, I go halfway. You always use the halfway, so halfway between 0 and 1/2 is 1/4. So I would say, okay, so f of 1/4, that's equal to negative 1.027. So now we've got a negative here. So now I know the root is somewhere between 1/4 and 1/2. So I go halfway in between there. So I go f of 3/8. So now I'm like, I'll even put it right here so it shows it's like right in the middle. F of 3/8, well, that's going to be 0.94067. The important point being it's positive. So now I know that the root is actually between these two numbers. It's between 3/8 and 1/4 because this is positive, this is negative. So then I would try f of 5/16, and you keep on going. Let me do one more step here. So f of 5/16, which again is right in between 1/4 and 3/8, halfway in between. This gives us a negative 0.0439. So we're looking for the input that gives us a 0, and we're getting there. We're getting there. We're not there yet, but we're getting smaller and smaller. So we would keep doing this. So now, since this is negative and 3/8 is positive, I would look for an input in between these two. And the input I would pick would be the halfway point. And you keep on going, and this number will get smaller and smaller and smaller. And as soon as your tolerance is met, like eventually it's going to be point positive or negative, but it'll be point something like 0.0000 and then some numbers. So you keep on going until that is as small as you need, and then you'll say that it would be the approximate solution or the approximate root between 0 and 1. And you can easily type this up. You can program it pretty easily, and it goes quickly, as you can imagine. The computer would converge on the answer to within the tolerance that you set pretty quickly. All right, let's take a look at another example here. Example 2 says, explain why the function is discontinuous at a equals -2. And you can see we've got a piecewise defined function. So this function f of x is defined to be 1 over x plus 2 if x is not equal to -2. Now you can see if you plug in a -2 here, it will be undefined. So then we also redefine this to be 1 if x equals -2. Okay, so if this function is continuous, if it's continuous at -2, then we know this has to happen, right? The limit as x approaches -2 of this function equals f of -2. So the limit is the same as if I just plug -2 into the function. So looking at this, f of -2 is 1, right? F of x is 1 if x equals -2. So we can see that looking at this, f of -2 equals 1. Okay, so far everything's good. Now we just have to take the limit as x approaches -2 and see if that also is equal to 1. So let's take a look. So this one we're going to have to approach -2 from each side, because we can see that this function, this part of it, when we take the limit, we're going to have a problem with just the -2, because we get this division by 0 here. So let's take a look. So if I take the limit as x approaches -2 from the left of this function, and we take the limit, so we have a numerator of 1, and just think as x gets really close to -2 from the left, so I'm going to make a little number line here to make it a little easier to work with. So we've got 0 here, we've got a -2 here. So as we are approaching -2 from the left, so we're coming in from the left, so these will be values like -2.1, -2.01, -2.001. So the magnitude will be a little bit bigger than 2, but negative. So that means that this denominator is going to be approaching 0 values. It's going to approach 0 values, but they'll be all through negatives, right? They'll be really tiny but negative values, because we're approaching -2 from the left. So we're coming in from here. So remember things like -2.1, 2.01, and so forth. So this actually is going to end up approaching negative infinity. Okay, so we could make this as a large negative as we want just by making this a small enough negative number. Okay, we can see there's already a problem here. This limit doesn't exist, right? Because remember, when a limit equals plus or minus infinity, technically it means it doesn't exist. But also there's something else here. If we take the limit as x approaches -2 from the right of this thing, okay, so now we're coming in from here. So these are values, numbers like -1.9, -1.99, -1.999 coming in here. These values have a magnitude less than 2, but they're negative, which means that this denominator is going to be really tiny but positive. The numerator is locked in at 1. These are going to be really tiny but positive values. So the limiting value of this is going to be positive infinity. So basically looking at these, we can see that the limit as x approaches -2 of f of x does not exist. This limit does not exist. One reason is the left-hand limit does not equal the right-hand limit. Another reason is they're both infinity. So the limit doesn't exist, which means that this can't hold, because this is 1 and this does not exist. So we could say, so the limit as x approaches -2 of f of x is not equal to f of -2. So this didn't hold. So that's why the function is discontinuous at a equals -2. So basically this here, this is our reason. I guess you don't need the so included, but this is our reason that it doesn't exist, and here's our argument to show that this is true. Example 3 says, use continuity to evaluate the limit. Well, using continuity to evaluate the limit is a pretty easy way to evaluate a limit. So we don't need to use limit laws. We just have to notice something here. This is an exponential function raised to a polynomial power. Well, polynomials are continuous everywhere. Exponential functions are continuous everywhere also. And this would be like a composition of functions. So this is continuous everywhere. So just to make a little note here, the exponential function is continuous. They're certainly both going to be continuous at 1, right? So exponential function is continuous. Also, the polynomial function. You don't have to actually have to write this. It's just a little note. So basically what that means is I don't need to use limit laws here. I can just plug 1 in for x. So I can just say this. So the limit as x approaches 1 of e to the x squared minus x, I'm just going to plug in 1. It's going to be the limit as x approaches 1 of e to the 1 minus 1, which is e to the 0, right? And this is just a constant, right? So I just plugged in the 1 here. I got 1 squared minus 1. 1 squared minus 1 is 0. E to the 0, we know that's just 1. And the limit of a constant is just a constant. So it's equal to 1. So we don't need to invoke the limit laws or do anything real complicated. We can just use continuity and just plug in the 1. Example 4 says, at what points are the functions continuous? Well, we know that these functions are all continuous on their domains. So basically we could think of this question as, what are their domains, right? At what points are the functions continuous? And if you look at these examples, these are all functions that are listed in those 7 types of functions that are continuous on their domains. So really, our goal here is just to figure out the domains of these functions. And those that will show at what points these functions are continuous. All right, so let's look at this first one, an example for part A. We've got this function here. So think about this one. What's the domain of this function? Just think, in other words, what could go wrong? So remember, domain issues, usually there's like a division by 0 or a negative under a radical, things like that. So just like in a algebra class where you were looking for domains of functions. So looking at this one, what could go wrong here? Most of you will probably see that we can't have a 2, right? F of 2 would result in division by 0. So here's how we can say the domain. There's a few ways we can say this. You could just say x is not equal to 2. What you're implying when you use this kind of notation is that all the other real numbers are okay. Here's a way to say this. Here's more of a fancy way to say it. This is the way that in the bad old days, when I was in calculus, it seemed like things were a little stricter. There was less applications and more theory, more rigor. So here's how we would say it back then. We'd say it like this. We use a set notation. So we're going to use what's actually called set builder notation. We'd say x is an element of, so you have that e, it looks like an e, but it's not really an e, but it means is an element of. So x is an element of the real numbers. And we have this scripted r, which means it's a real number. Then you have this vertical line such that x is not equal to 2 with the closed bracket. Really, these say the same thing. This is just a more formal way of saying it. We're saying it's the set of numbers where x is a real number such that x is not equal to 2. Now, a lot of times today, we don't really write all this. We just say this, x is not equal to 2, with the understanding that we're talking about real numbers and all other real numbers are okay. All right, so when you write it like this, let me just write this down. This is called set builder notation. Now, the most popular way to do this now and nowadays, is to use what's called interval notation. So I'll write it in interval notation next. Let's write this, interval notation. This is the way we typically do it now. So we say basically, on the real number line, I am going to start at negative infinity. I'm going to go to 2, but I'm not going to include 2. So I use a parenthesis instead of a bracket. And then a lot of times we'll use this union symbol. So we're saying that it's these numbers and also, because it's the union symbol, these following numbers. So we're going to start at 2 and then go to infinity and have a parenthesis. So when you use this interval notation, you basically think of the whole number line. Basically, isn't this saying every number in the whole number line except for 2? Because we go from negative infinity to 2, but we don't include 2, so we have a parenthesis. And then union 2 to infinity. So we're basically just plucking 2 off of the number line. So this is interval notation. This is probably the most popular notation nowadays. We just say this. So for this answer, most of you would probably either just write x is not equal to 2, or you'd say this with interval notation. I'd probably emphasize this notation because this is the one you'll probably see more often. But if you're feeling super fancy, you can use set builder notation, and it looks something like this. Okay, so for this next one, for part B, press pause, see what you come up with. Let's have you write it in these two ways, like this, and also with interval notation. So just take a few minutes, press pause, take a few minutes, come up with your answer, and then check back. Okay, you tried it, right? Don't just wait for me, you have to try it. Make sure you try it and then check back. Did you guys notice what just happened? That only happens when students don't try the problem first. So make sure you try the problem first. Okay, so hopefully that scary video clip scared the last remaining few into trying the problem first. And when you tried it, we would have noticed something about this. We have to just make sure that we can't get a 0 in the denominator. So we really need to solve this polynomial for 0 and then not allow any of those inputs. So to solve this, it's a second degree equation. Every second degree equation can be solved using the quadratic formula. Also, many of them and many second degree polynomials like this can be solved by factoring first. Okay, now this is one of those that can be solved both ways. But one thing we have to be able to do as a Calc 1 student is factor. And I've been teaching this long enough to know that some of us will still struggle to factor. We have to be able to factor. So if you want to be successful in calculus, Calc 1, Calc 2, all of them, you have to take the time to learn how to factor. So if you have a hard time factoring polynomials like this, make sure you look up like the AC method or the guessing check method. There's tons of videos out there. I know you've learned it before, but maybe you're rusty or never really understood it that well. But we have to be able to factor second degree equations, or it's just going to be a never-ending weakness that will catch up to you. So if you're rusty on factoring, make sure you practice. We have to be able to factor this or any factorable second degree equation. So for this one, as I mentioned, we could of course use the quadratic formula, but this one factors. So I'm just going to solve this by factoring. So what I'm going to do is like this, the guess and check or the standard method, where you basically do the FOIL method backward, right? So the FOIL method is the method we typically learn to multiply binomial times binomial. So if you think of doing it backwards to get here, so I know that first times first has to be x squared, so I'm putting x and x. Last times last has to be a 3, so there's really no choice here. It's just going to be 1 and 3. And then we know that outside times outside and inside times inside have to add up to a -4, all right? So if we make a negative here and a negative here, then it should work. So if I were to FOIL this, it means multiply these two binomials together, I should get back here. So then, if this times this is 0, the only way I can multiply two things together and get 0 is if one of them is 0, at least one, and it could be either one. So, of course, it could be that x minus 1 equals 0, or it could be that x minus 3 equals 0. In this case, x should be 1. In this case, x would be 3. So, what that means is we cannot allow this input, this x, to be a 1 or a 3 because it'll cause division by 0. So the way we can say this then, we could say basically the answer to this could be x is not equal to 1 and x is not equal to 3. Or if we wanted to feel, if we're feeling kind of fancy, we could use this set builder notation, say x is an element of the real number system such that x is not equal to 1 or 3. And then if you want to use the interval notation, which would probably be the best one, we basically have to start at the whole number line and just pluck out a 1 and a 3. So we're going to start at negative infinity, comma, 1, close parenthesis, union 1, comma, 3, close parenthesis, union 3, comma, infinity. So remember, the parenthesis means we didn't get there. We always have parentheses on infinities, negative or positive, because if we had a bracket, that means we actually got to infinity. And then you could say, well, how big is infinity? You would know because you got there. But remember, infinity is a concept. We never get there. So it's always an open or a parenthesis on infinity and negative infinity. So let me just mention one quick review. This doesn't have anything to do with this problem, but let's say we have 3 less than or equal to x less than 7. So just a quick review here. With interval notation, we would say we've got 3 and 7. We get a bracket on a 3 and a parenthesis on the 7. Because remember, interval notation says we want all the real numbers on this number line between 3 and 7, but including 3. We've got the bracket here, right? Because this says x is greater than or equal to 3. So the or equal to part, that or equal to gives us a bracket. Here, x is strictly less than 7, so we get a parenthesis. And that's where this comes in here. We basically are plucking out 1 and 3 off of the number line, so there's no brackets here. We go from negative infinity up to 1, but we don't include 1, so we have an open parenthesis. And then union 1, comma 3, so we go from 1 to 3, but we don't include 1 or 3, so we've got a parenthesis there. And then, so the same over here, from 3 to infinity. All right, enough of that. So we've got a couple more problems here. And when you look at part C, can you think of any inputs that would cause us any problems here? Think of the sine graph. Isn't the sine graph continuous everywhere? Doesn't just oscillate forever? There's no problems here. And this is absolute value function. It's continuous everywhere. So basically there's nothing here that could go wrong. So if the question is at what points are these functions continuous, well, they're continuous everywhere, right? So basically the answer to this, you could say all reals. Sometimes people say that. Or you could say x is an element of the real number system. Or in interval notation, you could just say negative infinity, positive, or comma, positive infinity. All these mean the same. And basically, it says that this function here, f of x, is continuous everywhere. So any of these answers would work. Okay, let's see what else we've got here. We've got a couple more. So let's have you guys take a few minutes, try them out, and then check back. Remember, if you don't try it out on your own, the angry Rottweiler face appears, and we don't want that. So make sure you press pause, try them out, and then check back. Okay, so with part D here, we can see there's definitely going to be a problem if our input is 0. Cosine is continuous everywhere, so there's nothing wrong with cosine, but we can't let x be 0 because we'll get division by 0 here. So basically what we could say here, we could say x is not equal to 0, again with the understanding that x could be any other real number, Or with interval notation, we could say go from negative infinity to 0, union, 0 to infinity. A little note too, this union symbol is not a U. It's not a letter U, right? So notation is important. This is a detail. Details are important. If I put letter U, that doesn't really have a meaning that we are trying to use. So don't use that. It's this symbol from set theory, right? This is this union symbol. Then the last problem here, we've got this function 2x plus 1 over x squared plus 1. And again, we basically need to make sure we can't divide by 0. But in this case, there's no way for that to happen, because if you try to set this equal to 0 and solve it, there's no real number that can cause that denominator to be 0, because you'd have to make basically x squared equal to negative 1, right? If that were negative 1 plus 1, you get a 0. So there's no way to do this. You could also subtract 1 from each side and get x squared equals negative 1. But if we're using real numbers, there's no solution here. So there's nothing that we could plug in here to give us a division by 0, right? Whatever you plug in here, you're going to square it, positive or negative. When it's squared as a positive. So the answer for this one is just going to be all reals, or negative infinity to infinity. All right, or I guess if you wanted to, you could say x is an element of the real number system. That works too. So any of those are just fine, and that should give you everything you need for section 2.5, which deals with continuity. But of course, you're ready for it now, but the only way you really learn it is you have to put in the work. So try the homework and let me know if you have any questions.